Hello, good morning. It is a pleasure to introduce you to a few questions in semiconductor engineering. Will be presented by Ms. Ashwini VR, myself, prepared by Ms. Naidile as well. Okay, we have the next question. The answer, I'm sorry, popped in already. Um, why is it that the pin diode is frequently used as not a voltage regulator, not a peak detector, not a harmonic generator, but a high speed switch? So the answer is that it is wide intrinsic semiconductor region. It has a wide intrinsic semiconductor region, a P and N semiconductor, which makes the diode an inferior rectifier but makes it appropriate for switches, fast switches, attenuators and photodetectors, and high voltage power electronic applications. To get high quality image, modern MRI systems use magnets. What kind? Semiconducting, B superconducting, C soft conducting, D insulating. The answer is superconducting, because these magnets are commonly used in MRIs. Next question. The energy gap in a semiconductor. A increases with temperature, B does not change, C decreases, D is 0. So the answer is decreases with temperature. The energy gap in semiconductor decreases with temperature. For a reverse biased PN junction, current through the junction increases abruptly as A breakdown voltage, B 0 volts, C 0.2 electron volts, D 0.7 electron volts. So let us see, in the reverse biased current through the junction, it increases abruptly at, in reverse bias. So this is the voltage we are talking about, and that is called as the A breakdown voltage. Next question. The common base DC current gain of a transistor is 0.96. The emitter current is 10 milliamps. Value of base current IB is A 0.4, B 9.6, C 0.96, D 9.04 milliamps. Answer is A 0.4 milliamps. Current gain is collector current IC divided by emitter current IE. So we have current gain given as 0.96 in the question itself. Emitter current is given as 10 milliamps. So we have only IC. Extrapolating IC, we get it as 9.6 milliamps. Now we have IC, but the question is IB. IC and IB are related by beta, that is, or sorry, IB is equal to IE minus IC. So you have 10 milliamps minus 9.6, 4 milliamps. In a semiconductor material, the energy gap between valence and conduction band is large, small, 0, infinity. Answer is small. Semiconductor material, the energy gap between valence and conduction band is very small, 1 electron volt. If the reverse bias is applied to PN junction, it is increased, then its barrier capacitance should increase, remain same, is independent of bias, or D decreases. The answer is decreases. Just like the capacitors, the reverse bias PN junction diode also stores electric charge at the depletion region. So as your depletion region thickens in the reverse biased condition, then the barrier capacitance should also decrease. In an NPN common base transistor circuit, if alpha is 0.95, IE is 20 milliamps, what is IB the base current? 1 milliamps, 19 milliamps, 21.05, D 0.1 milliamps. The answer is 1 milliamps. Current gain is collector current by emitter current. Hence, we have alpha 0.9 alpha given as 0.95. So we only have to calculate IC. Extrapolating, we get that as 19 milliamps. But we need to find IB. IB is IE minus IC. So we get it as 1 milliamps. A tunnel diode is a very heavily doped PN junction diode, a high resistivity PN junction diode, a slow switching device. It is used with reverse bias. Answer: a very heavily doped PN junction diode. Tunnel diode has very heavily doped PN junction that is about 10 nanometers wide. The heavy doping results in a broken band gap where conduction band electron states on N side are more or less aligned with the valence band hole states on the P side. The valence electron in a semiconducting material is 8, 2, 4, 6. The answer is 4. The electrons in the shell are the ones that form bonds with neighboring atoms. Such bonds are called covalent bonds. Most conductors have just one electron in the valence shell. Semiconductors, on the other hand, have typically 4 electrons in the valence shell. The capacitance appearing across reverse biased semiconductor junction increases with increase in bias voltage, decreases with increase in bias voltage, is independent of bias voltage, none of this. So we had seen a question. So the answer is decreases with increase in bias voltage. Reverse bias of the PN junction directly has a say on the depletion region. So when the width of the depletion region increases, the PN junction diode capacitance or the barrier capacitance will increase. So which of the transistor configuration is capable of providing both voltage and current gains? Common base, B common emitter, C common collector, D both common base and common emitter. So voltage as well as current gains. Answer is only common emitter. Both current and voltage gain can be described as medium, but the output is the inverse of the input, that is 180-degree phase changed. This provides a good overall performance, and as such it is often most widely used configuration. Tunnel diode characteristics differ from ordinary function diode characteristics in the respect that A. they are linear, B. they are non-linear, C. exhibit negative resistance region, D. none of this. C. they exhibit a negative resistance region. Semiconductors have dash temperature coefficient of resistance: positive, B negative, C both positive and negative, D none of the above. Answer is negative. A negative coefficient for a material means that its resistance decreases with an increase in temperature. Semiconductor materials carbon, silicon, germanium typically have negative temperature coefficients of resistance. Semiconductors have dash temperature coefficient of resistance. We have covered it. Inadvertently it is repeated. The answer is negative. Zener diode is used as A amplifier, B oscillator, C regulator, D filter. The answer is C regulator. BJT is A current control device, B voltage control device, C unipolar device, D none of these. Answer, it is current control device. Which of these is operated in negative resistance region as relaxation oscillator? A FET, B BJT, C UJT, D diode. Answer is C UJT. In PIN diode, the I stands for A insulator, B intrinsic, C impedance, D none of the above. Answer is B intrinsic. A PIN diode with a wide undoped intrinsic semiconductor region between a p-type semiconductor and an n-type semiconductor region. Resistance of a semiconductor exhibits positive temperature coefficient, negative temperature coefficient. Constant temperature coefficient will not depend on temperature. So the answer is that it is having a negative temperature coefficient. In case of semiconductor, the number of free electrons increases with increase in temperature, and as the number of free electrons increases, the resistance of this type of non-metallic substance decreases with increase in temperature. Hence, the temperature coefficient of resistance is negative. Answer is B, negative temperature coefficient. Knee voltage for germanium PN junction diode is 0.1 volts, 0.7 volts, 0.3 volts, 0.5 volts. Answer is C, 0.3 volts. The VI characteristic curve in forward bias. The parity voltage at the current starts increasing and it is called as the knee voltage. The value of knee voltage for silicon is 0.7, germanium 0.3. So find the value of beta if alpha is 0.85. So I have written the formula here. Beta is alpha by 1 minus alpha. So we need to find out beta. So typically we'll get 0.85 divided by 0.15. The answer would be 4.66, B 5.67, C 6.67, D 10.67. The calculator should give you an answer of 5.67. Current amplification factor in a transistor with common collector configuration is denoted by A beta, B alpha, C gamma, D delta. The answer is C gamma. The ratio of change in emitter current delta IE to the change in base current delta IB is known as current amplification factor in common collector configuration. It is known as gamma. The number of PN junction in a GUNN diode is A0, B1, C2, D3. The answer is C2. Number of PN junctions in a GUNN diode is 2. It is called as a transferred electron device. It is a form of diode, a two-terminal semiconductor electronic component with negative resistance used in high-frequency electronics. A MOSFET is dash control device, A current, B voltage, C power, D temperature. Answer B voltage. Field effect transistors are voltage control devices. By applying some voltage between gate and source, the drain current can be controlled. In order to control the operation of FET, the gain to drain voltage is varied to operate FET in the different regions of operation. Which of the following statement is true about FET? A. It has high output impedance. B. High input impedance. C. Low input impedance. D. It does not offer any resistance. The answer is A. It has high output impedance. Because of the silica insulator doped between the drain and the source, at the top the resistance offered by this is very high. The insulator will stop the flow, and there you have the answer. What is the main advantage of FET which makes it more useful in electronic applications? A. Voltage controlled operation. B. Less cost. C. Small size. D. Semiconductor device. Answer is it's small size. Because of its small size, the IC chips can be made even smaller, which reduces the wear and tear. The process technology used with a constant at which the ratio of width and length, the FET is more advantageous, and this is the primary reason. What is the value of drain current when VGS is pinch off voltage? So we all know what happens at pinch off voltage. So the question is, what is the value of drain current? The drain current is A 0 amps, B 1 amp, C 2 amps, D cannot be determined. So the answer is 0 amps. Pinch off voltage is defined as that VGS for which no drain current flows. The Shockley equation is AID is 1 minus VGS by VP whole squared. ID is IDSS into 1 minus VGS by VP whole squared. ID is IDSS into 1 minus VGS by VP. D ID is IDSS into 1 plus VGS by VP whole squared. So clearly Shockley's equation is B. Choose the correct statement. 1. The gate circuit impedance of MOSFET is higher than that of BJT. 2. Gate circuit impedance of MOSFET is lower than that of BJT. 3. MOSFET has a higher switching loss than that of BJT. 4. MOSFET has lower switching losses than that of BJT. So A, both 1 and 2. B, 2 and 4. C, both 1 and 4. D, only 2. Answer is C, both 1 and 4. So MOSFET requires gate signals with lower amplitude as compared to BJTs and has lower switching losses. In the transfer characteristics of a MOSFET, the threshold voltage and the measure threshold voltage is the measure of A, minimum voltage to induce a N channel to P channel for conduction. B, minimum voltage till which temperature is constant. C, minimum voltage to turn off the device. D, none of the above is true. So the transfer characteristic of a MOSFET, the threshold voltage is a measure of A, the minimum voltage to induce an N channel or P channel which will allow the device to conduct electrically through its length. How does the MOSFET differ from a JFET? A, JFET has a PN junction. B, they are both same. C, JFET is smaller in size. D, MOSFET has a base terminal. The answer is A, JFET has a PN junction. So MOSFET, it implies, is based on metal oxide layer that induces charge conduction, whereas FET is based on drift current, which is controlled by the channel width of the PN junction. The most commonly used method for triggering in SCR is A. Radiation triggering, B. Thermal triggering, C. Gate triggering, D. Voltage triggering. The obvious answer is gate triggering, C. So this is the most efficient method to turn on the SCR when the SCR is forward biased. A sufficient voltage at the gate terminal injects some electrons into the junction, say J2. This results to increase reverse leakage current and hence the breakdown of J2 even at the voltage lower than the VBO. It depends on the size of SCR. The gate current varies from few milliamps to 200 milliamps or more. If the gate current is more, then more electrons are injected into the junction J2 and results in the SCR coming into conduction state at a much lower voltage. A diac is turned on by A. Breakover voltage, B. Gate voltage, C. Gate current, D. None of the above. A. Breakover voltage. Most diacs have 3-layer structure with a breakover voltage of approximately 30 volts. Their behavior is similar to that of a neon lamp, but it can be more precisely controlled and takes place over a lower voltage. The triac is A. Like a bidirectional SCR, B. A 4-terminal device, C. Not a thyristor, D. Answers A and B. So the answer A, it is like a bidirectional SCR. The process of switching off a thyristor is known as commutation, triggering, rectification, saturation. The obvious answer is A, commutation. The turn-off process of an SCR is called as commutation, and it means the transfer of currents from one path to another. Commutation circuit does this job by reducing the forward current to 0 so as to turn off the SCR. Triggering means, on the other hand, to turn it on. Rectification refers to changing its waveform, that is a sinusoidal pattern, to a unidirectional DC. Saturation is when it reaches a peak value of output current. A diac is equivalent to a triac with 2 gates, diode with 2 resistors, pair of SCR, pair of 4-layer SCR. So I have given a picture over here for you to have a understanding of a diac. So what we have here is a pair of 4 SCRs. The answer is the answer is D. We have a diac, okay, a 2-electrode bidirectional avalanche diode, which can be switched from off state to the on state for either polarity of applied voltage. This is just like a triac without gate terminal, which is shown in the figure here. Its equivalent circuit is a pair of inverted 4-layer diodes. Passive component that cannot be fabricated on an IC. So passive components are resistor A, B inductor, C capacitor, D none. The answer is inductor. Components like inductor cannot be fabricated on an IC because the IC will be of very small, these components. For higher values, they have to be connected externally to the IC pins. The resistors, capacitors can be easily fabricated but not inductors. So the other drawbacks of monolithic ICs are that they have low power rating, cannot be used for lower power applications as they have a power rating more than 1 watt. The isolation between the components inside the IC is poor, and it is difficult to make the circuit flexible for any kind of variation. But the primary disadvantage of ICs are that you cannot have fabrications of component, a passive component like inductor. So for fabrication of integrated circuit, silicon is used because A, silicon is mechanically strong, B, silicon is more conductive semiconductor material, C, since silicon possesses characteristics which are best suited for IC manufacturing process, D, since silicon is black in color. Obviously the answer is C, since silicon possesses characteristics which are best suited for IC manufacturing process. What is the best choice for IC package used for experimental purpose? Is it a dual inline package DIP, metal can package, flat pack, or D, a transistor pack? So most often we have a dual inline package because it is easy to mount and the mounting does not require bending or soldering the leads. The silica layer in an IC acts like A, an insulating layer, B, conducting layer, C, barrier in the selective diffusion of impurities in epitaxial layer, and protects. D, both answers A and C. The answer is D, both answer A and C are right. Insulating layer as well as a barrier in the selective diffusion of impurities in epitaxial layer as well as protection. So a dual inline package is usually referred to as a DIP-N, N-DIP, DIP-N, all mentioned, all of the ones mentioned. Answer is DIP-N. A dual inline package is referred to as DIP-N, where N is the number present of the pin terminals of the IC. A device which converts electrical energy in the form of current to optical energy is called as A, optical source, B, optical coupler, C, optical isolator, D, circulator. So the obvious answer is that it is A. An optical source is an active component in an optical fiber communication. It converts electrical energy to optical energy and allows the light output to be efficiently coupled into the optical fiber. The frequency of the absorbed or emitted radiation is related to difference in energy E between the higher energy state E2 and the lower energy state E1. State what H stands for in the equation. E is E2 minus E1 is equal to HF. A, gravitation constant, B, Planck's constant, C, permittivity D, attenuation constant. The answer is B, Planck's constant. The difference in energy E is directly proportional to the absorbed frequency F, where H is a constant called Planck's constant. It's measured in joules per second, given by H is equal to 6.626 10 power minus 34. Okay, we'll move to the next question. An incandescent lamp is operating at okay. So a Ruby Maser amplifier must be cooled because Maser amplification generates heat. B, to increase its bandwidth. C, because it cannot operate at room temperature. D, to improve the noise performance. Obviously the answer is C, because it cannot operate at room temperatures. The microwave amplification by stimulated emission of radiation called as maser is very different from the laser operation, where flow of electrons in a crystal using a beam of electrons in vacuum. So the maser process may be quantified in terms of photons, and it operates at very high temperatures. The Ruby masers are very low noise preamplifiers used in the microwave receiving systems. They are cryogenically cooled to temperatures below 5 Kelvin, 5 degree Kelvin to achieve extremely low noise levels. A varactor diode may be useful at microwave frequencies, which is the false answer. So for electronic tuning, for frequency multiplication, or C as an oscillator, or D as a parametric amplifier. So you should choose the wrong answer, which is varactor diode will not be used as an oscillator. The diode whose internal capacitance varies with variation of reverse voltage. Such type of a diode is a varactor diode. It is used for storing charges. They are used as voltage control oscillators, RF filters, frequency and phase modulators, but not as oscillators. A ruby maser has a crystal of length 3 centimeters with a refractive index of 1.6. Wavelength is 0.43 micrometers. Determine the number of longitudinal modes. A. 1 into 10 raised to 100. B. 3 into 10 power 6. C. 2.9 into 10 power 5. D. 2.2 into 10 power 5. So this obviously depends on a principle. The answer given is D, but we need to know that the modes, number of longitudinal modes is given by Q is 2nl by lambda. What is Q? Q is the number of longitudinal modes, where n is the refractive index, L is the length of the crystal, lambda is the wavelength. So what do we have here? 2 into n. 2 into 1.6 is 3.2 into L, the length 3 centimeters. So you have 3.2 into 3 into 10 power minus 2 divide by 0.43 into 10 raised minus 6. So which happens to be 3.2 into 6 into 3 divided by 0.43 into 10 raised 5. So the answer is 2.2. So we come to the end.